So we're going to look at our next shortcut, which is quotient rule. This will be used for two functions divided by each other. So, of course, a quotient is division. Let me get set up here. The quotient is division. So we're looking for when one function is divided by another. We're talking about rational functions here. And to kind of show that it works, first we're going to find the derivative of this function using power rule. We'll do a couple rewrites, and then we're going to find the derivative of it using quotient rule. So the rewrite here on f of x is to write it as 2x to the third minus 3x squared plus 2. Each one, we're going to decompose that addition of fractions. Then simplify each term. Now this last term, I'll write it as 2x to the negative 2 so that I can apply power rule. So there's my power rule. If I rewrite, I get a common denominator of x to the third. I will get 2x to the third minus 4 over x cubed. That will be our derivative using a rewrite and then power rule. And so here comes that calculus beef. Got a little East Coast, West Coast beef here because the quotient rule was now first published by the other guy. So that's what that's about. I just think that's kind of interesting. Let's look at our quotient rule. Well, first of all, if we have a function defined as another function divided by another function, and whenever we have this, I have to give the caveat that the denominator, the function on the bottom, cannot be equal to 0. All right, so if we got one function divided by another, the way we find the derivative using quotient rule is going to be equal to, let's see, f prime of x times g of x minus f of x times g prime of x all over g of x squared. So that numerator reminds me of product rule. It's pretty much product rule up top. I've got two terms created, but the difference is I've got subtraction here instead of addition, which means it is not commutative. Commutative property does not hold here. So that means I can't get these backwards. I can't switch those around. I'll actually get the wrong derivative. So what you have to note is that the first term here, remember these are terms, this first term has f prime in it, the derivative of the numerator, and the second term has the derivative of the denominator. You do that and you're good. Derivative of the numerator goes in the first term, derivative of denominator goes in the second term. And then the bottom is just the denominator squared. You don't take the derivative or anything like that. Has a little bit to do with our common denominator work. That's how we get there. So now we're going to look at the same function and we're going to apply quotient rule. I meant to mention over here that if my numerator is to a power other than 1, like 5, we can't do this little method, by the way. You'd have to multiply this polynomial out by itself 5 times first. Then I could distribute that division to each term, and it's not going to be worth the time. So in this case, if I had to the 5th, I would just go to quotient rule right away. All right, so let's apply our quotient rule on this guy and see if we get the same derivative. All right, so the derivative is going to be the derivative of the numerator. Since it's a polynomial, a multi-term guy that I'm multiplying, I need to put it in parentheses. That is the derivative of the numerator times recopy the denominator. That's a monomial. I really don't need the parentheses. Minus recopy the numerator times the derivative of the denominator. Again, it's a monomial, so I don't need my parentheses. The whole thing over x squared. Normally, the way we're going to simplify this is trying to do some common factoring work, but we're trying to make this answer match our previous answer to display or demonstrate that it works. So what we're going to need to do is multiply everything out. So you can think of putting this in front. This is multiplication here, right? So I can think of commutative property. I can just switch these two things on multiplying. Sometimes that helps when people think about distributive property. So the x squared distributes, and I get 6x to the fourth minus 6x to the third. Here I'm going to switch these as well. So I'm thinking of this as negative 2x times 2x cubed minus 3x squared. When I do my distributive property, it's a little easier that when I distribute this 2x, I'm also distributing that negative sign with it. So it's easier to look at it how I wrote it up here above. Even if you don't rewrite in the future, it's just good to have that mental picture of that's what's going on here. So I get minus 4x to the fourth plus 6x to the third minus 4x all over x squared. Looking for common factors here, or common terms I should say, like terms. I've got 2x to the fourth. I've got my x third guys. Oh, that was a third. So those cancel, and then I've got my minus 4x all over x squared. That's our derivative. Did it match? It did not. Uh-oh. What did I do wrong? Oh, I did not square the denominator in my, I forgot this part. So this is going to be to the fourth, which will make this to the fourth. And then we can further simplify. Should have further simplified anyway. Now we need to notice that I can factor out an x in the numerator. I could factor out a 2 as well, but it's not going to really help us get to where making it match the other term. So I'm going to factor out just the x. So I've got the same exact derivative. So you can see that quotient rule works here. All right, so let's just start practicing quotient rule. Equation of the tangent line when x equals 2. So first I need the point of tangency. So this is g, not f. So I'm going to say g of negative 2 equals, plug that in. And we're going to get negative 5. So the point of tangency is negative 2, negative 5. Then we need to do the slope of the tangent line, which means we're going to take our derivative. So it's going to be the derivative of the numerator times recopy the denominator minus recopy the numerator times the derivative of the denominator, which is just 1. Times 1, I don't need to show that. All over the denominator squared. So now I am going to, normally we say we're going to simplify. I don't need to simplify here. If I'm plugging in an x value, it's best to just plug it in. Forget about the simplification piece. So I've got 2 times negative 2 plus 3 minus 2 times negative 2 minus 1 all over negative 2 plus 3 squared. And that all should work out to be a slope of 7. So now using my point of tangency and my slope of the tangent line, I could write the equation of the line. That's the equation of the tangent line. Show using the quotient rule that f of x equals that f prime of x. So they want me to do the derivative. Derivative of the numerator, it's got more than one term. So I'm going to put it in parentheses, times recopy the denominator, minus recopy the numerator, times derivative of the denominator. That's a monomial. I don't need the parentheses. All over the denominator squared. Simplification-wise, yeah, it looks like I'm just going to multiply these two polynomials together, those two factors. I'm going to multiply those together. So I'm going to get 2x cubed minus 2x plus 3x squared minus 3. And then minus, I'm distributing the 2x, but it's a negative 2x. Because of this negative, kind of sticks with it as I distribute it. So it's going to be negative 2x cubed minus 6x squared minus 4x all over x squared minus 1 squared. So now we're going to start collecting like terms. X cubed minus 2, those cancel the x cubed terms. X squared, I've got a negative 3x squared. Now I'm doing my x's. I've got a minus 6x and then a minus 3. And then I recopy that denominator. So here's the derivative I'm getting. It doesn't quite match the one that I have up here. So let's see if I can do some simplification here. Okay, well, first of all, I see an x minus 1 squared. So on the bottom, it looks like I can factor this into x plus 1 times x minus 1, which really becomes x plus 1 squared times x minus 1 squared. Now if we simplify the numerator, we can factor out a negative 3. And then if we factor the top further, this will be what? X minus 1. Oh, this should be a plus 1. And this should be a minus 2. Right? What do I have here? Wait, do I have this wrong? So let me start that over. When I factor out my negative 3, what do I get here? X squared, whoops, plus 2x plus 1. So then if I further factor it, it's going to be x plus 1 times x plus 1. So then there's a common factor here since it's all multiplication, and I get negative 3 over x minus 1 squared. So that is the derivative. I showed that f prime is that. So when we talk about a quotient rule, there's a couple things that are important that we want to talk about here. When you're going to do this quotient rule, there could be a lot of algebra happening. There's a lot of simplification after the fact. So you want to look at some of these rational functions. What if we can factor them to begin with and simplify them before taking the derivative? Right? So the bottom factors into that guy. The top factors to x plus 2 times x plus 1. Then we can cancel or divide out those common factors. And now we've got our original function as our rational function is now simplified, and doing and performing the quotient rule is a lot less messy. So now we do the derivative of the numerator, which is 1, times recopy the denominator minus recopy the numerator times the derivative of the denominator, which is also 1. I don't need to show those times 1s, right? All over the denominator squared. Now the simplification of this derivative is a lot less messy. So I've got x minus x cancels out. There's 0. Negative 1 minus 2. So I get negative 3 over x minus 1 squared. So we see that derivative again. So here's another way that we can do this derivative, right? And you can see that the algebra simplification is much better if you just think about possibly, can I factor and simplify before I start? So that is the lesson to be learned. If can factor and simplify the rational function go for it. I'll just say that this makes the simplification of the derivative much easier. Okay, so now we're going to use the quotient rule to do some derivatives here involving trig functions. Now that we have this rule, the only trig functions we know the derivatives of currently are sine and cosine. But now with quotient rule, we can derive some of our other trig function derivatives. And these will be derivatives facts like that you need to just kind of know. So currently we know that the derivative, remember that's a verb. That means to take the derivative of this expression. So we use this when we're only writing an expression, not an equation. The derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x. But what about our other six basic trig functions? What about the derivative of tangent of x? What about the derivative of cotangent of x? Cosecant. So there's six basic functions. Trig functions. We're going to do that now. So what we're going to do is we're going to rewrite f of theta as tangent of theta of sine of theta over cosine of theta. So let me try to say that again and see if it makes sense. We're going to rewrite f so that tangent of theta is rewritten as sine of theta over cosine of theta. Now that we have quotient rule, we can take this derivative. That was weird. I wanted to do that and then write theta. The derivative of the numerator times recopy the denominator minus recopy the numerator times the derivative of the denominator all over the denominator squared. I put parentheses here so that I remember that it's two things times each other. That's multiplication. If I didn't write the parentheses, it might look like it's subtraction and you think that you could subtract those. It is not. It's multiplication. So I'm going to rewrite the numerator by multiplying in each term what I can multiply. So I'm going to look in the first term here. I'm going to ignore the second term, and I'm just going to multiply what I can. Cosine times cosine is cosine squared. Now I'm looking in the second term, so I'm going to ignore the first term and multiply the negative sign times the negative sign. And I get a positive sine squared of theta all over cosine squared of theta. You cannot divide those and say it's 1 or they cancel. There's addition here. Don't do it. Got it? Jeez. Instead, we know that trig identity up top is just 1. Now we've got 1 over cosine squared. We can rewrite that as secant squared. We just derived the derivative of tangent. So the derivative of tangent, I'll write it out a little better actually at the bottom. So it's easier to probably write it down here. The derivative of tangent of theta equals secant squared of theta. Now look what I did here. It was a mistake, but I caught it. I want to say the derivative with respect to x, but then I go use thetas. Can't do that. Everything's got to match. This is now a fact you're going to kind of have to know. The derivative of tangent is secant squared. All right, let's do another one. Let's do cotangent. If I rewrite cotangent as cosine over sine. I can do my quotient rule. The derivative of the numerator times recopy the denominator minus recopy the numerator times the derivative of the denominator all over denominator squared. If I look at my first term and multiply what I can multiply together, I get a negative sine squared theta. If I do the same in my second term, I get a minus cosine squared theta. I want to factor a negative 1 out of my numerator so that I can use a trig identity. So I get negative 1 over sine squared theta because this is our Pythagorean identity, which is equal to 1. And then I bring the sine squared up, and I get negative, what is that one? Cosecant squared theta. So now I know the derivative, with respect to theta, of cotangent of theta is equal to negative cosecant squared theta. So that's another rule I now know that you're going to be expected to know. I now know the derivative of tangent is secant squared, and I know the derivative of cotangent is negative cosecant squared. Those are similar. They have similar structure. It's a trig function squared. It's a trig function squared, right? So they're similar. One's positive and one's negative. We can talk about why that is. What else? You got your secant versus your cosecant. We could talk about why that is too. Just important ways we can kind of remember these derivatives. Let's try secant now. If I rewrite secant as 1 over cosine, I can then apply quotient rule to that guy. So now f prime is 0 times recopy the denominator minus recopy the numerator times the derivative of the denominator. Those parentheses are important because of that minus sign. It shows that it's multiplication, not subtraction. Over denominator squared. Whoops. It's not x. I get 0 minus a negative times negative, so it's actually plus sine of theta over cosine squared of theta. So we're going to think of that as sine of theta over cosine of theta times 1 over cosine of theta. So we can rewrite it as tangent of theta times 1 over cosine is secant of theta. So now we know the derivative of secant. The derivative of secant is equal to secant theta times tangent theta. Now we're going to do cosecant. Same kind of thing here. So we're going to go 1 over sine of theta on our rewrite, and now my derivative. Oh my gosh, I did it again. The derivative of the numerator times sine of theta, which is the recopying the denominator, minus recopy the numerator, times the derivative of the denominator, all over denominator squared. If I simplify, I get negative cosine of theta over sine squared of theta. Look, you guys got to be writing these all the time. I don't want to write them right now either, but got to do it. So I'm taking the time to do it. You need to do the same. Okay, so then I'm going to break these up again like I did before. I can call it cosine of theta. I'm kind of decomposing the multiplication here over sine of theta times 1 over sine of theta. This is negative cotangent times 1 over sine is cosecant. Okay, so then it's multiplication. It's negative 1 times cotangent times cosecant. So I could kind of rewrite these in any order I like. So I'm going to change around the order a little bit. So, sorry about that. So then I'm going to say that the derivative of this one was cosecant equals negative cosecant cotangent. Notice that the structure is the same as this guy. They kind of stick together. We can discuss why that is. You got one trig function times another. Same thing here, except you got the negative version. Notice that it's the derivative of secant starts with secant. The derivative of cosecant starts with cosecant. Of course, one's positive, one's negative. That'll just help us remember them. So now I know the derivative of all 6 basic trig functions. When I remember that, I have these 2, and now I know these 4 new ones. All right, so now we're just going to practice some quotient rule here. Can I simplify and solve to start? If I factor out an x, I get what, x minus 2 over x plus 2? No, I can't simplify. So I don't like factored version for finding derivatives. I like it when it's multiplied out. This version is better than that version. Whoops. All right, so the derivative, I'm not using this version, is the derivative of the numerator times recopy the denominator minus the numerator times derivative of the denominator, which is 1, all over denominator squared. Simplifying, we are going to multiply stuff out in the numerator. So we get 2x squared plus 4x minus 2x minus 4 minus x squared plus 2x all over x plus 2 squared. Did I miss? Okay, no. I was thinking I missed something. So the 2x squared, the 2 minus 2x plus 2x, those go away. 2x squared minus x squared is x squared. So I did those already. And then the 4x is still there. Minus 4 over x plus 2 squared. That's our derivative. Is that what they're asking for? Find the derivative. Yes. Okay. P prime of theta. The derivative of the numerator is cosine of theta times recopy the denominator, theta squared, minus the numerator, recopy it, times the derivative of the denominator all over the denominator squared. Simplification-wise, we've got theta squared. I'm just going to rewrite each term, clean it up. So I'm going to switch that multiplication. Minus, I'm switching this multiplication. And then squared is to the 4th. I can factor out, typically now, this is what I was talking about before, typically we want to look for a common factor if we can't multiply stuff out and then simplify like we did on this previous one, right? Where we multiplied stuff out and then canceled. Typically we want to look for a common factor. So I'm looking at both of these 2 terms and seeing what they have in common. It looks like they both have a theta that I can factor out. This has a theta squared and that has a theta. Remember, you can't touch these thetas in here. They're part of the trig function. So I'm going to take theta and divide it out of, if I just pay attention to the first part. If I divide theta out of the first term, I get theta times cosine of theta. Now, if I just pay attention to the second term and divide out my theta, I get negative 2 sine theta. All over theta to the 4th. Why is it nice to factor out in this quotient rule? Typically, whatever you factor out should be able to divide out with one of the ones on the bottom. So now I'm left with theta cosine of theta minus 2 sine of theta all over theta cubed. All right, let's work on this guy. H prime of theta is derivative of the numerator times recopy the denominator minus recopy the numerator. You'll be hearing this in your sleep. And then times the derivative of the denominator. So I like to do brackets here when there's multiple terms. Derivative 1 of 0, derivative of cosine is sine. So in this case, I didn't need those brackets. It didn't turn out to be multiple terms. It was just one term. All over the denominator squared. So what are we going to do here to simplify? We can multiply stuff out. I can multiply this times this, the cosine times that function, and then I can multiply the sine times the sine. So I'm going to get cosine of theta minus cosine squared of theta minus sine squared of theta all over 1 minus cosine of theta squared. Once I start seeing trig functions squared, I start thinking Pythagorean identities. Can I turn that into cosine squared plus sine squared somehow? Or sine squared plus cosine squared, same thing? Looks like I can. I can do this. I can go cosine of theta, factor out a negative, and it would be cosine squared of theta plus sine squared of theta all over 1 minus cosine theta squared. So this is our Pythagorean identity. So now I get cosine of theta minus 1 all over 1 minus cosine of theta squared. Now, what's interesting? It feels like those should cancel, like they're almost the same, but the signs are different. Like cosine minus 1 versus 1 minus cosine. They feel the same, but they're not quite the same. So what we can do is we can factor a negative 1 out of the top to make them the same. Whenever they're like the signs are opposite, if it's subtraction and you just kind of switch them, right? That means if you factor a negative out of one of them, I'm going to write out each step. Now they're the same thing. I'm going to break apart the bottom for a second just to show you what's going on here. Right? I'm going to, instead of writing it as squared, I'm going to write it as 1 times itself. This is now the same thing as one of these. So I can, it's all factored, I can cancel it out. Because if I rewrote it, it would be negative times 1 minus cosine of theta. I can just switch it around, right? I can rewrite the 1 there and then minus cosine second, and then it's very clear that it crosses off with one of these on the bottom. So this is now negative 1, and I have one of those left on the bottom. So it's negative 1 over 1 minus cosine of theta. Once again, folks, it's really about the algebraic simplification afterwards. The calculus was done right here, from this step to that step. It wasn't really horrible. All of this is your algebra simplification skills. All right, so we're just going to continue to work on them. All right, let's work on this guy. Let's see what we have here. This one probably would require a rewrite. I'll get a common denominator of x in that numerator and combine it. So I have 3x minus 1 over x plus 5. Then if I rewrite again, it's 3x minus 1 over x times 1 over x plus 5. Then I can multiply the denominator. So when we were doing limits, I was saying do not multiply out the denominator. For derivatives, you don't want to leave it factored like this. When you're going to find a derivative, you want to multiply stuff out. So it's going to be x squared plus 5x. That's the easiest way to find the derivative. When I have to do the derivative of the denominator, I want to have it written as x squared plus 5x. Now I can do my quotient rule. Derivative of the numerator times recopy the denominator minus recopy the numerator times derivative of the denominator all over denominator squared. Let's simplify. We multiply and we multiply and then collect like terms. 3x squared plus 15x minus 6x squared plus 15x minus 2x minus 5. I'm not going to take a whole step to distribute this minus sign. I'm just going to know that each one of these signs are different. Start collecting like terms. I got 3x squared minus 6x squared gives me a negative 3x squared. Now I'll do my x's. 15x minus 15x is 0 minus 2x, so that's a plus 2x. And then I've got plus 5. We can pretty much leave it here. There's going to be some weird like multiple choice. If this doesn't answer the multiple choice answers that you see, maybe you can factor further, things like that. Maybe you can simplify further. If you can simplify further, we would do that. But just factoring this, I don't know if it's considered simplified, but we'll look at it. So you can factor out a negative sign first of all to make it a little easier to deal with. Then I can factor this 3x squared minus 2x minus 5 into what? 3x minus 5 over x plus 1. Then on the bottom, you've got your x squared plus 5x squared. I mean, I could factor a little further. I'm going to just leave this. Nothing's going to cancel. I would accept, in this case, either one of these because I'm factoring, but nothing's canceling. So I'm just going to say that the original box up here is good enough. Okay, now how do we do some of this with like a graph, if we include a graph in there? So we're going to define r of x as cosine of x divided by this graph. Is the graph of Rx increasing, decreasing, or neither increasing nor decreasing at x equals pi? Show your work and justify your reasoning. So this is going to mean that if r prime of pi turns out to be a positive number, I know that when the derivative is positive, r is increasing. So then I know it's that. If r prime of pi, if the derivative at pi turns out to be negative, then I know r is decreasing. If it comes out to be 0, then it's neither, or undefined, then it's doing neither. So that's what we're going for here. So we want to take the derivative of r by doing quotient rule. Derivative of the numerator is negative sine of x times recopy the denominator, f of x, minus recopy the numerator times the derivative of the denominator, all over the denominator squared. Now, simplification, we're not really going to get into it because we're just going to plug in pi anyway. So sine of pi is 0, so this will be a negative 0, which is just 0, times f of x. So 0 times f of, what am I plugging in, pi? Oh, sorry. So 0 times f of pi is 0. I don't need to really figure out what f of pi is. Minus cosine of pi times f prime of pi. I'll just write it out. It might be a little easier. Over f of pi squared. So now we're going to go through and simplify this stuff. So we end up with 0 times f of pi is 0. Minus cosine of pi is negative 1, so that becomes a plus 1, times the derivative of f at pi. So if I go to pi, that's like right here, it's 3.14. And I go to the derivative at that point. The derivative means the slope of the graph, which looks like that slope is down 1, right 2, down 1, right 2. So it looks like it's negative a half all over f of pi. So not the slope of the graph there, but what's the actual y value at pi? Well, pi is somewhere around there. It looks like it's almost negative 3. I mean, I don't know exactly what it is, but I know that it's a negative value, and then I'm squaring it. I don't really care about the number. I care about more, is it positive or is it negative? So up top, I've got 1 times negative a half is a negative number, divided by a negative squared, which is a positive number, so I'm getting a negative number. I know r prime of pi, the derivative at pi, is negative, which means that r of x is decreasing when x equals pi, because r prime of pi is less than 0. That's what we want to say. Okay, now can we do some of this stuff from the table? Similar to product rule. I'm not going to explain the table. I did that the other day on product rule. Estimate the value of g prime of 2.5. So g prime of 2.5, remember, just a little practice when we're doing tables. To approximate a derivative from a table, 2.5 falls in between those two x values. So if I do the secant line with an x value on either side of it, on either side of that x value, that's going to get us an approximation of our tangent line. So we've got g of 3 minus g of 2 all over 3 minus 2. So g of 3, I'll keep using approximates, I guess. G of 3 is negative 3. G of 2 is negative 1 all over 3 minus 2. So it's going to end up being negative 2 over 1. So the tangent line, or the derivative of 2.5 at 2.5, is approximately negative 2. Remember that the secant line is an approximation. If you choose points on either side, the closest points is really what you should do. All right, let's go this way. We'll do this one next. So now they're going to define p of x as g over f. What's the value of p prime of 4? So that means we need to find the derivative. So p prime of x is equal to derivative of the numerator times denominator minus recopy the numerator times derivative of the denominator all over denominator squared. So that means p prime of 4 is going to be equal to g prime of 4 times f of 4 minus g of 4 times f prime of 4 all over f of 4 squared. So now we're going to use the table and grab those numbers. So g prime of 4 is going to be, g prime is negative 2. F of 4, so we're at 4, we're just always in this row, right? F of 4 is 1, minus g of 4 is 7, times f prime of 4 is 8, all over f of 4, which is 1, squared. So we want to simplify that number. 50, negative 56, negative 2, negative 58 over 1. So that's negative 58. What does this value say about the graph of p when x equals 4? So we would say since p prime of 4 is less than 0, the p of x is decreasing at x equals 4. All right, 2 more to go. We're almost done. 46 minutes. All right, now we're looking at this derivative here. So what do we want to do here? It's a couple ways you can look at this. Man, we could do product rule here. Oh, man. Okay, so this is not going to be fun. I see one function times another function. What I'm considering is like which way I want to do this, but I'm going to do it as a product rule here. So this is my first function, that's my second function. Move this down a little bit. Product rule says derivative of the first times recopy the second plus recopy the first times derivative of the second, which is now going to be quotient rule. So you have a quotient rule inside of a product rule. Whoops. So it's going to be derivative of the numerator times recopy the denominator minus recopy the numerator times derivative of the denominator all over the denominator squared. All right, so now we're not going to simplify because they want us to plug in 2. So it's going to be 4 times 2 times f of 2 over g of 2 plus 2 times 2 squared all over f prime of 2 times g of 2 minus f of 2 times g prime of 2 over g of 2 squared. Now I can either simplify the numbers that I can or go get numbers off the table. So I'm going to get 8 times f of 2 off the table. Hold on, I'm going to pause this. Okay, I grabbed these off the table. I'm just going to kind of zip through some of this here, and you can verify as you pull it off the table. So let's see here. It was 8, and then that part is going to be 2 over negative 1 plus 2 times 2 squared. And now these numbers in here is going to be negative f prime of 2. Wait, I think I did that backwards. F prime of 2 was 9. Yeah. So it's going to be 9 times negative 1 was my g of 2 minus negative 1 times 2, yep. Make sure those are right. G prime of 2. G prime of 2 was negative 1. So, yeah, I had those the other way. So minus 2 times negative 1. I'm just reading these off the table, so you can go get those on your own and see if you get it to match. Over negative 1 squared. I just have to simplify that number. It's going to simplify to negative 72. I've already worked it out. Okay, let's do this last one. Find the equation of the tangent line to the graph. Again, we're using the table. So v prime of x, actually maybe we should do the point of tangency first, is v of 3, which is 3 times 3 over g of 3. So I get 9 over g of 3 off the table is negative 3. So negative 3, so my point of tangency is 3, negative 3. Now I need the slope of the tangent line, which means I need the derivative of v. So it's going to be the derivative of the numerator times recopy the denominator minus recopy the numerator times derivative of the denominator all over denominator squared. So now I need v prime of 3. So I get 3 times, what's g of 3? I should write this out. 3 times g of 3 minus 3 times g prime of 3, a lot of 3's, all over g of 3 squared. 3 times g of 3 is negative 3, of course, a lot of 3's, minus 3 times g prime of 3. G prime of 3 is 6. Hey, we got a 6 in there. All over g of 3, which was negative 3, right? So g of 3 squared, because I see that it matches this guy. So I see that number there. Okay, that whole thing is going to work out to be negative 7. So now I'm going to write the equation y plus 3 equals negative 7 times x minus 3. There's the equation of the tangent line. That is it.